A random variable becomes data once you observe it. So, as I said, if I toss a coin to see if it's heads or tails, before I toss it, it's a random variable. As soon as I toss it and see it was a tail, it then becomes data. So data and random variables are related to each other. Okay? So I don't know, as I said, how much sleep you get. Okay? So I don't know how much that is. I don't know how much Towson students get for sleep, how much the average student gets for sleep. If I go out and start asking students, can you record for me how much data or how much sleep you get? And so what you do is when you go to bed, you mark down what time it was, and then when you wake up in the morning, you mark what time you woke up. Then it becomes data at that point. Okay? So there's this link between random variables and data, that any data actually kind of starts off as a random variable. So if I'm looking at housing prices start off as random variables. I don't know how much I have to sell for. I actually don't know how much until it finally goes through the sale process and everyone agrees to a price and it gets sold. So that's what we mean by a random variable. Now, random variables come in two forms. One is what's called a discrete random variable. Discrete random variables are a lot of fun. A discrete random variable is a random variable you count. So if I ask you the question, how many traffic lights did you stop at on your way from home to school? That is a discrete random variable. You can tell me you stopped at no traffic lights, that you stopped at 1 traffic light, that you stopped at 2 traffic lights, you stopped at 3, whatever the number is, but you can count those outcomes. Okay? You don't talk about that I stopped at 2.5 traffic lights, unless if you kind of slowed down and then went through a red light or something like that. Okay? But you don't talk about that. If I ask you, how many siblings do you have? Again, that's something you count. You can say I have no siblings, or I have 1, or I have 2, or whatever that number is. And the other part about that is, let's say if you tell me that you have 1 sibling, you have a brother or sister. I can't rank the people who have 1 sibling in any order. They all have 1 sibling. I can't say, well, your brother's really cool, so we're going to put you ahead of the person who has, the kind of strange sister or something like that. You don't do that. You all have 1 sibling, and you're all in the same group, and so there's no way of ranking you within that group. So lots of variables are discrete. Discrete random variables are a lot of fun. I wish if we were doing a different course, we could spend a lot more time talking about discrete random variables. Discrete random variables give you the binomial distribution, which gives you monkeys typing at typewriters producing the works of Shakespeare. In terms of, could monkeys actually type out the works of Shakespeare, and how many monkeys would you need to have doing that for how long? And it gives you all types of neat things. And as I said, binomials are used with coin flips, so anything that has kind of a yes-no characteristic falls into this. Where we're going to spend our time, though, is continuous random variables. Continuous random variables are variables that you measure. So I could ask you the question of, how long did it take you to drive? I could ask you, how much rainfall have we got, or how much snowfall have we got in Baltimore this winter? I could ask you, how tall are you? These are things that I measure. And the idea with this is, if I were to ask you how tall you were, you might tell me, I'm 5'9". Okay. And you're not lying to me, you're actually telling me your real height. So it isn't like a person who says they're 6'2" and they're really 5'4" or something like that. Okay. So you're telling me the real height. But really, when you tell me that you're 5'9", what you're telling me is that you're somewhere between 5 feet 8.5 inches tall and 5 feet 9.5 inches tall. That you're somewhere in that range. Okay? Because I could take 2 people, you both say that you're 5'9", you're both right, you're not lying. But I could bring you up both to the front of the classroom, have you stand back to back, And we would say that one of you was taller. Okay. Now, it might be just by, a wee little bit, but we'd all agree that we could say that one was taller. And hypothetically, we could take everyone in this classroom and literally start you from smallest to tallest in this class. That's a continuous distribution. Okay? A continuous distribution, you could say that two people are the same height or the same weight or anything like that, but we'd actually detect minute differences. This is why in the Olympics, with some of the swimming events and speed skating, they break it down to sometimes thousandths of a second. Okay? Because they're trying to get finer and finer and finer measurements. Because 20 years ago or 40 years ago, Michael Phelps in that race where he touches just like a split second before the other guy, they might have called that a tie because in the old timing system with old timers where it was sometimes tenths of a second or hundredths of a second, they were the same. But one was just a little bit faster than the other. So we're going to be interested in these continuous random variables, variables that we measure. So we're going to be interested in them. And basically, with them, they fall under the normal distribution. The normal distribution is the granddaddy of all distributions. Not sure if we'll have enough time today to talk about why it's kind of the biggest and the most important of the distributions for probability. If we don't talk about today, we'll talk about next class when we talk about sampling distributions, which is where it really comes into play. But the normal distribution is the one that's most universally used in all of statistics. So what we think about the normal distribution, it's a continuous distribution. So it measures ranges here. Is bell-shaped or symmetrical in nature. And this is where it gets its second name, the bell curve, which is different from the bell jar. But the bell curve, or normal curve, is the idea of this, is it's a symmetrical distribution. You're equally likely to be above or below the mean or the central tendency. But not only that, but the idea with the bell part is that you're much more likely to be near the central tendency than away from the central tendency. Okay? So whatever that central tendency is, you're much more likely to be near the central tendency than far away from it. So again, if I were thinking about maybe you driving to campus, okay, what it says is if you think it takes you on average 20 minutes, that your spread away from that 20 minutes is much closer to where that central tendency is. It isn't like it normally takes you 20 minutes, but some days it takes you 5 minutes and other days it takes you an hour. That basically you're normally maybe within 15 to 25 minutes is your average range. Any questions so far? So we have this.